So today we're going to hear from Professor Mike Behrenfeld about the NAAMES study. But before we get going and before I introduce Mike, we generally like to go through just a quick reminder of what CLIVAR does and what PSMIP specifically is tasked with doing. So US CLIVAR, the goal of US CLIVAR is to foster understanding and prediction of climate variability on intraseasonal to centennial timescales through observations and modeling, with an emphasis on the role of the ocean and its interaction with other elements of the Earth system. We aim to serve the climate community and society through coordination and facilitation of research on outstanding climate questions, and also to coordinate and advance research within the US to improve documentation, understanding, modeling, and prediction of variations in global and regional climate. So the Process Study and Model Improvement Panel, otherwise known as PSNIP, our mission is to reduce uncertainties in the general circulation models used for climate variability prediction and climate change projection through an improved understanding and representation of the physical processes governing climate and its variation. And so our terms of reference include reviewing, prioritizing, and coordinating relevant process studies, climate process teams, and other investigations that lead to improved parameterizations and better quantification of model uncertainties, improved climate model fidelity, and validation of observing systems. So we have a strong connection between the modeling and the observational communities in the work that we're doing. We also need to develop and encourage mechanisms to further the development and implementation of timely, relevant process studies and a research strategy. So that's very community-based. And we advise US CLIVAR on research priorities and identify research gaps and develop milestones to promote funding opportunities. So we aim to help foster and coordinate joint agency participation to support these activities. And finally, we liaise with other US CLIVAR panels and working groups to ensure model process studies and model improvement needs are considered in their efforts. So I'm just going to stop sharing now and hand it back. And so today we're going to hear from Professor Mike Behrenfeld, who is a professor in the Department of Botany and Plant Pathology at OSU. He did his MS and PhD at OSU, went on to Brookhaven National Labs, then Rutgers, spent some time at NASA Goddard, and then returned to OSU as a professor. He is the lead PI on the NAAMES project, which has brought together atmospheric scientists and plankton ecologists, surface ocean, physical oceanographers, and I'm looking forward to hearing your talk, Mike.
Well, thank you, Sophie. Can you hear me?
Yes.
Okay. All right. Well, thank you guys for the opportunity to present to you. As mentioned, I'm going to be talking about the North Atlantic Aerosol and Marine Ecosystem Study. And I know that the way you guys normally do this is you have an observationalist talking first and then a modeler. Unfortunately, you're stuck with me today. The primary person on the team that was doing or responsible for larger scale coupled ecosystem modeling was Scott Doney, and he wasn't able to participate today, so sorry about that. All right, so just kind of a brief overview of the NAAMES project. NAAMES was motivated in part by earlier satellite observations regarding phytoplankton blooms and the processes, the physical and biological processes that give rise to blooms and define the annual cycle of plankton in bloom forming areas. Primary phases of this are the declining phase, which happens in the autumn, disturbance, which initiates the bloom, a recovery period, and the recovery here is the coupling between phytoplankton division and loss rates that ultimately leads to a climax in a bloom before the subsequent or the following decline. So NAAMES set out to try and evaluate ecosystem interactions with physical oceanography during primary phases of this annual cycle. And the second primary overarching motivation was to evaluate seasonal impacts of marine plankton on aerosols and clouds, motivated by contrasting earlier findings from different ocean regions. And the idea here being that biological activities in the ocean give rise through bubble bursting and wave breaking to biogenic compounds that influence aerosols in clouds. The NAAMES project, if you're not all aware of this, is already complete. We did our final report out to NASA headquarters in November of 2019. It was a very large undertaking. End to end, there were over 270 people involved in the project. What I'm showing on this slide are this is the science team, and names shown in black text are investigators that were on the original proposal. And once that was selected, I went out and actively solicited other people to join, with some funding from NAAMES, some funding from other agencies, and to try and fill in some of the additional holes in the project that I thought were going to be important. In total, there were 37 additional scientists added to the NAAMES project post-selection. The various stars are just pointing out people that played specific roles in the project. Bolded names are team leads, and yellow highlighting was our ecosystem modeler in his group, Scott Doney. So the overall strategy for the NAAMES project was we were intending or focused on doing 4 field campaigns, each one of them about a month in duration, and each one of them targeting a specific element of the annual plankton cycle. The idea was to characterize the state of the ecosystems during a given campaign and not necessarily do them in a specific order. So we had the flexibility of ordering the campaigns during the 4 different events in any way we wanted to, which gave us a lot of flexibility, and that was a good idea. One of the things we also did is the plan for the project was to do 2 campaigns and then have an intermission year where we were able to, look at lessons learned, figure out what we wanted to change before doing the final 2 campaigns. And that intermission idea was also a good idea. The top left graph has a background of surface chlorophyll seen from space, and the black triangle looking shape there is the nominal cruise plan. So we were located in the western side of the subarctic Atlantic. The right-hand graph is showing in a red line the satellite observed net rate of phytoplankton accumulation in biomass. So a value of 0 means that biomass is not changing. That's the straight black horizontal line. Data below that represents a decline in biomass, and blue shading represents periods of blooming. One of the advantages of the way we set this up is the primary science transect is the north-south black line you see on the left. And that section was occupied over a period of about 2 weeks. But the timing of blooming events in the subarctic Atlantic varies from the south to the north. So by taking advantage of that latitudinal gradient in timing, we were able to capture essentially 2 weeks or 2 months of variability in ecosystem states in a 2-week window. During each one of these campaigns, primary sources of data came from measurements on a ship. The RV Atlantis was used for all 4 campaigns. BioArgo floats, which we deployed during all the first 3 campaigns, and used not only to continue observations when we were not occupying stations or between campaigns, we also used them to identify stations, primary stations during subsequent campaigns. So we would go to a station and have some history on what had happened there before we got there. These field measurements were coupled with airborne measurements on a NASA C-130, and of course we had a variety of different satellites providing observations. One of the targets for the C-130, in addition to making flights over the ship, was to underfly the Calliope LiDAR, and we got some additional funding for additional flight times from the Calypso program to do these underflights. There was a wide range of observations or measurements conducted during each of the NAAMES experiments, ranging from phytoplankton stocks and rates and community composition, measurements of physical, chemical, and optical properties, aerosol and cloud microphysical properties, measurements to track the influence of continental or anthropogenic influences on aerosols, marine aerosol precursors and sea air transfer. So we were looking at precursors in the water and doing C-suite measurements to look at primary emissions, as well as aerosol gas composition. In addition to in situ measurements on the aircraft, we had 4 remote sensing instruments. These were the high spectral resolution LiDAR, HSRL, from the Langley group, a research scanning polarimeter from the GIS group up in New York. GeoCape was our ocean color sensor. Schwan Min's group was the primary group working on those data. And then an upward looking sky spectrometer. Just to give you some orientation on the deployments, what I'm showing here is the 4 NAAMES campaigns. The background color is sea surface height anomalies, illustrating, as you might expect, the very dynamic physical environment that we were sampling in. Lots of eddy features. The black line in each one of these is showing the cruise track of the ship. The heavy black circles are the primary sampling stations, which targeted anticyclones, cyclones, and in between eddies. This graph is showing the deployment of the floats. There were a total of 19, what was it? No, that's the ships. There was we deployed floats on the first 3 campaigns. I don't remember actually which ones, how many we did in total. But in this graphic, the dashed blue line is the ship transect, and the black circles, again, the primary sampling stations. The stars are where the floats were deployed, and then the lines, the wiggly lines, show the trajectory of those floats over the course of the NAAMES campaign. In total, we did 32 stations, primary stations, sampling 7 cyclones, 8 anticyclones, 17 stations outside of the eddies, and we had 19 stations with floats deployed in them, for a total of 30,000 kilometers of ship track. During the ship track in between stations, of course, there were a lot of continuous measurements being made. In this graph, again, the dotted blue line is the ship transect, and the solid lines are the flight patterns, or the flight locations. Each color represents a different flight. This is for each of the first 3 campaigns. The aircraft failed us in campaign number 4, and so we don't have any science flights during that campaign. We did a total of 5 underflights of calypso measurements, satellite calypso measurements. We flew over 19 of the float locations, visited 54 stations, a total number of visits of 54 of those stations, and collected data over tens of thousands of kilometers of surface area. When the airplane did visit a ship station, it flew a predefined pattern that included high altitude flights, spirals through the atmosphere, low altitude flights, in this kind of Z scheme that we developed for the station observations. With respect to data, all of the NAAMES science data are already made publicly available through a number of different locations. When NAAMES was selected, NASA headquarters decided to assign 2 DACs for data archive for the project. Atmospheric data is archived in the ASD AC DAC, and the ocean biology and ocean data are archived in CBAS. Argo are the profiling float data, and the IFCB plankton imaging data are not compatible with these 2 DACs, and so those are archived in the Argo GDAC and EcoTaxa, respectively. We also developed a very information-rich website. This was built by the team at Langley, and you're welcome to go take a look at that if you're interested. Lots of very interesting information there. and public outreach as well. We did a lot of public outreach. I don't have any material on that in my primary slides, but I have a fair amount in my backup if you're interested during our discussion to see some of those things. In terms of scientific outcomes, to date, NAAMES has approximately 90 publications, another 7 papers in review, and I know a number of other papers that are in the works. You can look at these publications, each one of them, if you're interested, going to the NAAMES website, clicking on the Science tab, and then Publications. We published an overview of the NAAMES project in 2019 in Frontiers. And in 2018, I did a paper with Emmanuel Boss, essentially overviewing the state of thought on phytoplankton blooms and annual cycles, if you're interested in that overview. We also did a special issue in Frontiers. They call them Research Topics in Frontiers, with 21 contributions and a summary editorial that was just published this past year. Over the course of the project, there were over 200 presentations done, posters and talks at various meetings, and as I mentioned before, a major public outreach effort throughout the project. So what did we learn? NAAMES provided very strong evidence supporting what we call the disturbance recovery hypothesis regarding blooms. Most of this evidence came from the NAAMES study and data collected in the subarctic Atlantic. But we also extended the analysis to the Southern Ocean, taking advantage of the SOCM program down in the Southern Ocean. And what we find is that the same basic processes take place over the annual cycle in both regions, but of course there are some differences due to different forms of limitation on plankton growth. The NAAMES project, one of the things that we found during NAAMES, which was a surprise to me. I expected to go up into the subarctic Atlantic during the peak of the bloom and see big diatoms, and we didn't. We didn't see big diatom blooms. And so that led to a lot of questions and thought about, well, what are the factors that determine whether diatoms, large diatoms, are going to be prominent? And what is the evolution of the diatoms? What are the keys to succession? And these ideas on succession led to what I call a new mandala on plankton succession, which also gave some insight on factors controlling phytoplankton size distributions. From those two bits of thought and research, we proposed a solution to Hutchinson's plankton of the paradox. It was published in ISME this last year, in case you're interested. One of the things that was very interesting to me was that we got data, we have data that suggests that the life cycle of, or the lifestyle of viruses, phytoplankton viruses, is likely more tempered than lytic in nature. And I thought that was rather interesting, with the lytic lifestyle being triggered by host stress. Right now I'm working on a concept of neutral theory applied to phytoplankton communities and trying to understand phytoplankton biodiversity from a neutral perspective, and that's ongoing work. We gained a lot of insight on sub-mesoscale structuring of plankton and marine animal communities. There were a number of algorithms developed, some of those focused on retrieving phytoplankton community composition from hyperspectral data with applications to the upcoming NASA PACE mission. A lot of measurements were done on phytoplankton grazer-virus relationships, so there's a lot of data on that. Craig Carlson was leading his group on looking at carbon cycling through the bacteria plankton. One of the very interesting things that we got lucky with on NAAMES is that kind of a key element in this disturbance recovery hypothesis is that physical processes can lead to a disturbance in the coupling between phytoplankton predators and the phytoplankton growth. And during the second NAAMES campaign, we got to actually witness a disturbance event right before our eyes. We had a storm come through, and it caused about a 30-meter mixed layer to deepen to over 200 meters and then re-stratify. So we got to see the plankton become disturbed and then recover again, which was very lucky and very cool, and a number of papers came out of that. Another kind of side shoot of NAAMES was during some of the night ops, we were looking at vertical migrations of animals. And this led to an idea about trying to measure the diel vertical migration, or DVM, from space using a satellite LiDAR. And we were successful in doing that. And a paper came out on that about a year and a half ago. And we also used satellite LiDAR data to extend our results for the North Atlantic to both the North and South polar regions as a whole, and look at decadal scale changes in annual cycles in those two regions. The NAAMES study also provided information on aerosol cloud interactions and remote sensing of cloud droplets, a large part of that coming from the aircraft data. We had scientists, as I mentioned before, looking at the seasonal production and consumption of in-water volatile organic compounds to a degree that I don't think has been matched in the past. We did find a significant impact of ocean biology on secondary aerosols, although the role of ocean biology on primary aerosols, at least as observed by sea sweeps, seems to be of second-order importance. We see a significant contribution of ocean biology to atmospheric dimethyl sulfide concentrations, which I think is consistent with previous observations. And then there was an offshoot study from NAAMES looking at changes in subarctic Atlantic productivity over the entire industrial era using methanosulfonic acid as a tracer. Okay, so that's kind of a general summary, and I don't think I used up my 30 minutes, but certainly open to discussion.